Okay, so we're going to finish up the notes on circular motion, at least the first part and some of the circular motion examples. We're going to pick up where we left off. To test your understanding, you have two coins that are on the same rotating turntable. All right, you've got to remember what's going on. It says one is 10 centimeters from the center, the other is 20 centimeters from the center. Which coin travels faster in speed? In other words, length per time. Well, let's remember that V is equal to omega times R. So the one that has, as R goes up, V goes up. So the one that has the longer radius, which would be coin B, okay? In the same amount of time, in other words, in the same angular rotation rate, V is higher because that length is longer that it has to travel over the end. Which coin has the greater angular speed? Well, it's the same for both of them. All right. In other words, if they're rotating on a same rotating turntable, omega is just equal to 2 pi over the period, right? So they both move the same number of radians, which would be theta, in the same time. This is also, remember, equal to the change in theta over the change in time, okay? Now, student A passes student B in the same track, then passes line 2 also at the same time, and then they go around the right semicircular section. All right, it says which student travels the fastest speed. Okay, well, if they both hit this at the same time, then if they're both going at the same rate when they hit this guy goes this far, this guy goes this far, okay, they go the same length. If they're going the same length in the same period of time, same length over time means the same speed. Okay? Which student has the greater angular speed? Well, I mean, I want you to think about it. If this guy is going the same, and we consider this the center of the circle, the distance from here to here, this would be theta sub 1, but the distance from here to here is clearly, which is theta sub 2. Well, theta sub 2 is less than theta sub 1, which means that since omega is the change in angle over the change in time, and the time period's the same, then we have to know that runner B has an omega that has a angular speed that is less than runner A. So who has the greater angular speed? A does, because he travels a greater angle in the same amount of time. Okay? Now, we've talked about this one already sort of in class. Test your understanding. A car with a smaller radius wheel and a car with a larger radius wheel cross the line at the same time. They travel a straight road and cross another line 100 meters away at the same time. So they're covering the same distance in the same amount of time. So what do you know? Same velocity. Which wheel has the greater angular speed? Okay, well, the one with the greater angular speed is going to be the smaller wheel. Think about it. V equals omega R, so omega is going to equal V over R. So as R goes down, omega goes up. So the smaller wheel has the greater angular speed. Kid's tricycle has one big wheel in the front, two small wheels in the back. all right, which has the greater angular, greater linear speed, excuse me. Which one has the greater linear speed? Well, since all of the wheels cover the same amount of distance in the same amount of time, since they're all attached to the same frame, they have the same velocity, okay? They have the same velocity, and the explanation is the same distance. The same amount of time, delta t, okay? Now, two small wheels have the greater angular speed, right? If they have the greater angular speed, they need to rotate more times to cover. If they're smaller, they have to rotate more times to cover the same distance. And we see that. Okay? Right now you're moving 100 miles per hour because Earth is rotating about its axis. Would people in Texas be moving faster or people in Alaska? I have to tell you that if you're talking about the axis, rotating about its axis, Alaska's here, Texas is here. That means that Texas is further from the pole. So R of Texas is greater than R of Alaska, right? Think about it. And since who's moving faster, if we look at V equals omega times R, then as R goes up, the velocity goes up, doesn't it? So people in Texas are technically moving faster because the Earth is moving faster there. Right now you have a linear speed, v, sub u, in hundreds of miles per hour, and angular speed, omega sub u, about the Earth because the Earth is rotating. The moon also has a linear speed, v moon, and angular speed, w moon, or omega moon, excuse me, about the Earth's axis. Which is greater, your angular speed or the moon's angular speed? Well, think about it. Let's talk about the period. Period of the Earth is 365 days. That is clearly greater than the period of the moon, which is 28 days, right? Oh, excuse me, rotation. Thinking rotation, not about the sun. It rotates about its axis in 24 hours. However, the moon rotates about the Earth, which is what we're looking at, because we're looking about the Earth's axis. It's 28 days. So clearly, I got to change this then. Clearly, the period of the Earth is less than the period of the moon. All right, well, we know omega is equal to 2 pi divided by the period. So as t goes, what, up? Omega goes down. So if the moon has a greater period, it has a lower angular rotation rate. So u, which one is greater? Well, this should be u, I guess. You do. Okay. Which is greater? Your velocity or the moon's velocity? Well, v is equal to omega r, right? But here's the problem. I know that your omega is higher, but what I don't know is the radius, right? Because you have a higher omega, but the moon has a higher r. So we don't know which one affects it more because we don't know exactly what those numbers are. So I need more information. Speedometer on your car is attached to the axle of your car. It's not attached directly to your car's wheels. Friend has a car with 20-inch wheels, calibrated for those wheels. The speedometer measured 60 miles per hour. The car moved 60 miles per hour. Friend replaces all of his wheels with 24-inch wheels, but didn't change the speedometer. Now, when his speedometer measures 60 miles per hour, what's his car doing? Okay, so we know the speedometer is measuring omega directly and uses V equals omega R, since it's measuring a rotation rate, omega R to tell the speed. So if R goes up, V is also going up, okay? So if the wheels are 20% bigger, then your speed is 20% faster than the speedometer actually says, okay? How is velocity directed when an object travels along a curved path? It is tangent to the path. What does that mean? That means that if we have something moving with a velocity this way, if we have something moving, I should put this better. If I have something moving in a path that's like that, at any point the velocity is tangent to that path. So here, velocity would be this way, there, here, the velocity would be this way. So the velocity is curving. So how can an object have a constant speed and yet be accelerating? Well, acceleration, if you get it, is the change in velocity over the change in time. Velocity isn't changing because it's got the same velocity at constant speed, but what is changing, and remember, velocity is a vector. It has speed and direction. So while the speed is not changing, look at those vectors. The direction is changing. So this thing does have acceleration. So A sub c is what we call centripetal acceleration. This is the speed something has as it changes direction. We defined A sub c as the velocity squared over the radius, or as omega squared times r. If you plug in omega r for v squared, you get omega squared r. Now, we have a concept map. How are all these related? We know that t is equal to 1 over f. This is going to summarize everything we've done so far. T and omega is going to be, omega, if you remember, is 2 pi divided by the period, okay? Omega is also equal to 2 pi, then, because those are reciprocals of each other, times the frequency. Omega and A sub c, we know that A sub c is equal to omega squared r. We also know that V is equal to omega r. That's between omega and V and centripetal acceleration, A sub c is equal to V squared over r. Now V and T are related through the period. Again, if omega is equal to 2 pi over T, then V is equal to 2 pi r over the period. And notice that the frequency and the centripetal acceleration are not related, at least not directly. Okay. All right. So now as we look at this, oops. So, example here. If we're going to look at this diagram and see what's going on, it wants us to draw, for each pair of vectors, draw them to scale and draw the change in velocity between them. So between v naught and v sub 1, we know that v naught is up 2 over 2. Up 2 over 2 is v naught. We know that v sub 1 is up 1 over 2. So up 1 over 2 puts it here, which means that the change in velocity would be v sub 1 minus v naught, which would be this way. This is my change in velocity. Okay? And what direction is the acceleration? Acceleration is downward. Every object, since it's projectile motion, the acceleration is downward. It's gravity, isn't it? Okay? So now, v sub 1, up 1 over 2. V sub 2 is straight across. So what we notice is that that change in velocity again, from one to the other, is going to be that way, again. Are you seeing a pattern here? V sub 2, V sub 3, change in velocity again. It's looking the same every time. Acceleration is downward. Acceleration is downward. In other words, that the acceleration direction is the same as the direction of the change in velocity. Wow, imagine that. I'll let you finish the last one. Now it says, draw in what you know the acceleration is for each one of these. Okay. So V naught is by looking at the change in velocity, because what did we just find? The acceleration's in the same direction as the velocity, change in velocity. So this one's up 4 over 2. I got this one, V naught. I've got V sub 1 is up 2 over 4. This way. So I know my change in velocity is this way. Change in velocity is that way. And it wants us to draw that. Change in velocity is right here. So this is my acceleration vector. And I want you to look at where that thing is pointing. Boom. If we do this again, we're going to see the same thing. We're doing V sub 1, up 1 over 2, or up 2 over 4. V sub 1, V sub 2 is just straight over 4. So my change in velocity is this way, which means that my acceleration is this way. Okay, what does that mean? If you'll notice, it's going to be the same for all of these here, and then this guy's going to be going this way if we follow it through. So what do you notice? All of them are pointing towards the center of this circle. Okay, what direction is every object acceleration? Acceleration is towards the center of the circle. Okay, so now, circular motion examples. What we know is a couple of things. Draw the forces. One of the things you need to understand is the force F net is going to, F net, or which of course is your sum of forces, is always points towards the center. Same as the acceleration does. The other thing you need to know is you need to know right here that there is never to represent centripetal force. Centripetal meaning centered, what? Centerward, towards the center. There's never a force arrow to represent centripetal force. Centripetal force is a made-up force. It is representing the direction of that circular acceleration, but you do not put it on the graph. So if I talk about the Earth orbiting the sun, draw a gravitational force on the Earth. Well, the gravitational force on the Earth is here, towards the center. That is not, notice it doesn't say F sub C. If we have a ball whirling, the tension would be this way, F sub T. Ball rolls around a vertical track, draw the normal force. Normal force, of course, is going to be towards the center. Car goes around a curve, draw the frictional force. Well, if you're going around a curve, your car wants to go this way. So the force of friction is going to be in the opposite direction towards the center of the circle. Electric force is towards the center. Over the top of a hill, we have mass times gravity going this way. And we have the normal force going this way. Notice that the mass times gravity is longer in this case as we go over the hill than the normal force is. If we have a rock on a string moving in a horizontal circle, that means it is going this way around the circle. What do we have going on? Well, we have a tension force going this way. So what do we have? We have a component of that tension force that goes what? Towards the center of the circle, and a component that goes this way. Because think about why we have a component going that way. Because on this ball, we also have mg, don't we? So these two red vectors are the components. This would be F sub t cosine theta, and this, of course, would be F sub t sine theta. Because my acceleration is what? In every one of these pictures, where is my acceleration? My acceleration is going to be towards the center. Acceleration towards the center. Acceleration towards the center. Right? Acceleration towards the center of the circle. Acceleration towards the center. Acceleration towards the center on all of these. Ball rolls along a dotted path inside of a cone. Draw the weight and the normal force. Well, the mass we know, of course, is mg down this way. Where's the normal force? Well, normal force is going to be this way, right? But what do we know? We know that we are going to have some sort of a normal component of that force headed towards the center of that circle. So this is going to be force normal times the cosine of theta, whatever this angle theta is, okay? And then we have a component this way that cancels out the normal force times the sine of theta, that cancels out gravity, okay? So, write an expression, an equation for the biker going over the hill. Well, the biker going over the hill, we say that the sum of forces is going to be m times a centripetal. So this is a centripetal force. Well, we know what a centripetal is, don't we? A centripetal is v squared over r. So we plug that in. So we know ma sub c is going to end up being mv squared over r. So this mv squared over r is equal to the forces acting towards the center, which in this case is mg, minus the forces acting away from the center, which in the case of the biker is the normal force. How about the rock on a string? Rock on a string, we still know the sum of forces, since it's moving in a circle, ma sub c is going to be mv squared over r. So that mv squared over r is going to be equal to, in this case, the forces acting towards the center of the circle. Well, what's the forces acting towards the center of the circle? That's only the force of tension times the sine of theta. Now, what's acting in the other direction? Well, that would be the force of tension cosine theta acting up has to be equal and opposite mg, which is your normal force, or sorry, your gravitational force acting downward. Now, ball in the cone. Ball in the cone. We again know that the sum of forces, centripetal, mv squared over r. So this mv squared over r is equal to what's acting in the same direction, which would be the normal force times the cosine of theta. I'm sorry, sine. What did I do? It's up here. This is the angle. This should be cosine. This should be sine. I'm sorry, guys. This should be normal force times the sine of theta. And we know that mg is equal to the normal force cosine of theta. Okay? How do we construct a Newton's second law equation for an object moving in circle? Forces towards the center minus forces away from center equals mv squared over r. Okay, so let's look at a couple more examples. We've got a car going around an intersection, making the turn. The car can either make a left turn or a right turn as shown. Assume the car approaches, makes the turn, and continues forward, all without changing speed. So it has a constant velocity. All right. Right. Does not mean it doesn't have acceleration, though. It's got acceleration because it's going around a circle. Okay. This is a circular motion. All right. The centripetal force is provided by the force of static friction. In other words, for this car not to slip going around that circle, it has to have friction of the tires with the road. And that relationship is mu times the normal force, right? Okay. Why is it static friction and not kinetic friction? Well, it's static friction because the car is not sliding. Remember, kinetic friction only takes over once something starts to slide. So tires with the road is always a static friction issue, not a kinetic friction issue. So what happens if mv squared over r is greater than mu sub s times the normal force? Well, force of friction, if it is less than the net force centripetal, the car slides. Okay? So, we know that the force of static friction, which is going to be what? Mu times the normal force, has to be less than or equal to, because this is always the static friction is less than or equal to, the sum net force centripetal, which would be mv squared over r. Okay? So we know this has to be the case for the car to not slide. Wait a minute. To slide. Boy, I'm having trouble here. To slide, it has to be less than. So to not slide, it has to be what? Greater than. Okay? Okay. Which turn, left or right, requires the car to slow down more in order to make the turn safely? Well, which one has the greater radius? the right turn, if you look here, the right turn right here, if we're going to the right, it has a much smaller radius. So r to the right is less than this radius right here. This is r to the right, this is r to the left. So how does that affect the speed? Well, let's look. What do we know? We know that mv squared over r has to be what? Less than or equal to mu times the normal force. Well, normal force of this car is just going to be mg, isn't it? So that leads me to believe that mv squared over r has to be less than or equal to mu times mg. Well, the mass goes away. Mass doesn't matter. So what we're trying to figure out is v. So v has to be less than or equal to mu rg. It's v squared. So we're going to take the square root. So we get v has to be less than or equal to the square root of mu rg. So for v to be safe, what has to happen? Well, if r is smaller, look at the relationship. It's direct, isn't it? As r goes down, v goes down. In other words, that's a tighter turn, isn't it? It makes sense if you think about it. The tighter turn would require you to slow down more. So the right turn since its radius is smaller. All right, bicycle and a rider of mass m ride over hill with radius of curvature r, okay, with a constant speed v. So that combination of a radius and a constant speed tells me we are dealing with sum of forces centripetal. It's over the hill, right? Okay, so what do we know here? We know that we have some radius r here, okay? It's going at some constant speed v this way. All right, so what are the forces acting on this thing? Yeah, let's do those in a different color. Or better yet, let's do it this way. If we have sum of forces here, we know we have mg downward, and we have a normal force upward. And I'm going to make the mg arrow longer than the normal force because some of it's causing there to be a centripetal net central directed force, okay? So we also know the acceleration is this way towards the center of the circle, okay? So what do we know? Let's use our formula. We know this is equal to mv squared over r. And we know that we need to set that equal to, looking at what we said before, how do we solve these problems? Forces towards the center would be mg minus forces away from the center, which would be F sub n. Okay? So if we want to find the normal force, derive an equation for the normal force, then all we have to do is put normal force on one side. We're going to add normal force to one side and subtract to the other. We get that the normal force is equal to mg minus the net centripetal force. And there's our equation. M is in both of them, so we pull that out, and we get g minus v squared over r. So that's our new normal force. If it takes the car 3 seconds to make a left turn without changing the speed, what's the period of the car's circular motion? 3 seconds to make the turn. Well, if it's making a left turn, that is 90 degrees or 1/4 turn, correct? Okay, so the period would be the amount of time it takes for it to make an entire 360. So there are 4 quarter turns, 4/4, so 4 times that 3 seconds would be, it takes 12 seconds to go all the way around. So our period is 12 seconds. All right. Getting close to the end here. We have an accelerometer placed on a car, so we are looking at the acceleration, centripetal acceleration versus the time. All right, so what we are seeing is we have a certain acceleration, pretty much 0 here, and then jumping to a little bit above 5 here, and then back down, okay? Car's initially traveling along a straight path at a what? This is moving pretty much at a, since it has 0 acceleration, we know it is moving at a constant velocity. All right, so what would the graph of the acceleration along the y-axis look like as a function of time? So, well, what evidence from your question or statement would happen? So it's going to be a flat line at 0, right? Then we know it makes a 90-degree turn. So it's going straight right here, and now it's going straight here, and now it's turning here from 2 to 5 seconds. Okay, well, remember, y-axis acceleration is a tangential acceleration. So is the tangential acceleration going to change at all? No. So this y-axis acceleration, now you may not understand this, but this is what you need to understand here. And I'm going to put this out here. At any point, and you have a car moving with a velocity, if it has acceleration, that acceleration, it's got acceleration towards the center of the circle, that's centripetal. If the speed is changing, if it's not moving at a constant speed, then you've also got acceleration moving tangentially. But because this is a constant speed, so this would be my y-axis, and this would be my what? X-axis speed, if you're kind of thinking about this, since it's centripetal acceleration, is my y-axis acceleration. It's the tangential acceleration. Well, if this delta v is not changing, then this tangential acceleration is always going to be 0. So the y-axis acceleration is going to equal 0 the whole time. Okay? This is the acceleration along the x-axis is our centripetal acceleration. That's what tells us that this is y-axis tangential and x-axis centripetal, okay? And what indicated that? It says that, it said that the, it's not changing tangentially. Which is indicated as our y-axis speed. Does the car make a left turn or a right turn? It makes a 90-degree turn. It doesn't tell us what's going on. But if the centripetal acceleration is in the x-axis direction and it goes positive, this is a positive x direction. If it is a positive x direction, that means that it must be turning in the positive x direction. And you see right here, positive x direction means it must be turning that way, which is to the right. So it's turning to the right. Positive x direction is towards the center of the circle. So A sub c points that direction. Okay? Use the graph to determine both the speed of the car as it turns and the radius of the turn. Well, we know the period is what? It's going a quarter turn in 3 seconds. So we know 4 times that 3 seconds. And how do I know it's going a quarter turn in 3 seconds? Because it's a 90-degree turn between 2 and 5 seconds. That's 3 seconds. And 90 degrees turn, right turn is 90 degrees, so that's a quarter of a turn. So we know the period is 12 seconds. Well, and we know what? A sub c, we can find that from the graph, 5, 6, 7, 8, 9, 10. So it tops out here at 6. So my centripetal acceleration is 6 meters per second squared. Okay, so what do we not know? We don't know the radius of the circle. We don't know the velocity. So let's figure it out. We know that the velocity is equal to 2 pi r divided by the period. We also, however, know that a sub c is equal to v squared over r. Okay, so let's solve for one of these and plug into the other. So let's solve for v squared. Let's take this one and say, okay, v squared is equal to a sub c r. So what do we know? Or better yet, we already know what v is. Let's take this v and plug it in right there. So what do we know? We know the centripetal acceleration is equal to 4 pi squared r squared over t r. So this r is going to get rid of one of those r's. So we have 4 pi squared r over t is our centripetal acceleration. Well, I know that's 6. This is 4 pi squared. T is 12. I can solve for r, and I get a radius of approximately 22 meters. Well, if I know the radius, then I can find the velocity by plugging in. And I'm going to do that using this equation right here. So using this equation, I get v squared equals a sub c times the radius. So v squared is equal to 6 times the radius, which is 22. Take the square root of both sides, and I get a velocity that is approximately 11.5 meters per second. All right. Why is there no centrifugal force? Centripetal force and centrifugal force are different. Okay,